Doing.
So we talked about how this rate of still might go if you had C components last time, and we noticed that it's a very simple problem, except the calculation is probably tedious. Probably has to be done mechanically. And so you don't learn anything doing that. What you really want is a formula so you can see what's going on. So let's see if we can get some formulas for various cases. And the simplest case is C equal to 2. And our equations are, in the plain vanilla case, something that looks like this, which is L dx dl equals y minus x. Nice thing about C equals 2, well, I guess when I'm doing C equals 2, I ought to kind of tell you that x is equal to x1, 1 minus x is equal to x2. x1 is the more volatile. And 2, of course, is the less. So everything's been defined now. So here we are. We now have a problem where we can do something. So we have dx over y minus x equals dl over L. We integrate this and we find that log L over L0 equals the integral from x0 to x of dx over y minus x. So it's the basic equation in a plain vanilla case, and what it tells us is that it's one equation in two variables. One equation in two variables. And the two variables are x and L. So this is an equation that if you input an x, you can calculate an L. If you input an L, you can calculate an x. That's the view of this equation. One equation in two variables. Now, it may be that you want L. It may be that you want x. It may be that you want other things. So the first thing to do is to decide how we're going to look at this equation. And we'll look at it as follows. We will say, of course, y and x are in equilibrium. So I need, what do I need here? I need y as it depends upon x. But here's y as it depends upon x. For this x, that's y. So y minus x is this distance right here. So what I would do is, I would say, oh gee whiz, clearly the thing to do is to plot 1 over y minus x versus x from x0. Straight from there, draw yourself a curve, might look like that. And then if somebody says, oh, I'm going to give you x, give x, that puts a point here. It's the x he gave you. You want to know L? Calculate this area. And the log of L over L0 is minus that area. So that's how you get L if you're given x. If you're given L, that means you know the area, so you got to find the x where you would stop. So plot the same thing, 1 over y minus x versus x. Here's x0. Somebody says, oh, okay, I'm going to give you L. That means you know this area, so you begin calculating this area as a function of x. And when you get this area right, you have the corresponding x. So I can get x versus L or L versus x, all from an equation like this, which I can handle pretty easily. Question is then, what kinds of problems can I solve? So let's list some problems we can solve. Now, you got to understand that the way this goes is, I start here with some L0 and some X0. I run for a while. I've separated that into an L and an X here, and into a T and a Y average here. I dump that, that's my bottom's product. I dump that, that's my top's product. So I take this L and X0, run for a while, separate it into two pieces, dump it, I've got my two problems, I go run again. Okay, so the question becomes, how do you find Y average? How do you find recovery? And stuff like that. So, but we know how to do that. We do that like this. So, I guess we think that, Y average times T equals X0, L0 minus XL. And I guess we think that T is L0 minus L. So if somebody says run this to the end, so this is the start. You go through a bunch of intermediate stages, and this is the end. Dump that, you got your two products, you go do whatever you want to do. So the question is, if L is an well, we're pretty much always going to assume that L0, X0, equilibrium curve are given. Do I need to know anything? Well, yeah, of course, P, because that's what got us the equilibrium curve. Somebody inputs an L. If you input an L, then you've got a T from there. If you've got a T, you've got to take this L, and you've got to go find X from that equation. And if you've got a T and an X and an L, that gives you Y average. And if you want the recovery, it's Y average T over X0, L0, which, according to this, is equal to 1 minus XL over X0, L0. So I can get everything I want going in that direction. And if somebody were to give me an X, I would go find L. So here we inputted L, and we got everything we might want. If I input, well, it's more likely somebody will input a recovery. So suppose I input a recovery. And my aim is to find out at what L I should end this. So I say, okay, I got this recovery, do I? That means I've got Y average T over, over X0, L0 equals 1 minus XL over X0, L0. Now, is that enough to do anything? I'm inputting this. I find this. That tells me XL at the end of the run. That's good. Surely for every X that I might be interested in. Now, what am I inputting? I'm inputting recovery. It gives me that. I have these equations. That's where that came from. So what on earth have I got? Well, I know I can plot out the XL curve from here. So solving this equation, I get the L versus X equation. I get something or other, however it goes, L versus X. But I look along there for the point at which XL is equal to the value that I know it has to be. That gives me X and L. I guess I can go back and calculate everything else I want. So given the recovery, actually given X is much easier. Because, okay, I did this for given L, that was easy. If I were to give you X at the end of the run, if I give you X at the end of the run, then I go over here and get L. Okay, let's list our cases. There's a lot of cases. If I give you L, I input L, then I go get X. Once I have L and X, I can get everything I want. So then I just go get everything. Conversely, if I input X, I get L. Now I got X and L again, so it's the same calculation. I can get everything I want. I guess it's a little trickier to input Y average T over X0, L0, because that would give me XL over X0, L0. So I would know the product X0 is XL, XL is known. So I could plot L versus X, be a curve like that. Now all I gotta do is go to my equation which says log L over L0 equals the integral from X0 to X of dx over Y minus X, which gives me L versus X. Put that on here, however it looks, probably it looks something like that. That gives me L and X. I go solve my problem. So the C equal to 2 case, you can pretty much get everything you want. There's even a simpler subcase where you don't even have to do any graphical work. And that is this. Suppose I have a dilute problem. Maybe I'm trying to boil phenol on water. Question?
Yeah, I just was curious, the integral, is that a dx or a dt over y minus x?
Tell me what board you're pointing at, left or right?
Board, we most recently wrote.
This board or that board?
The right board.
Right board. Where am I to look?
Right where your right hand is.
Right here?
Right. No, lower.
Here?
Right. Or lower. To the right.
Here?
Yeah, is that dx or dt?
This is log L over L0 is the integral from x0 to x of dx over y minus x. I wrote that down because I had erased it before, but look. It's interesting you would ask a question about that. How careful do you guys want to be? You got the integral from x0 to x of dx over y minus x. Some people would find that disturbing. Do you? Do you realize that this x is a variable I'm interested in, and that x are dummy variables in integration so that I don't have to invent a whole lot of new variables? Great. So we'll be careless. We wouldn't worry about dummy variables of integration. Like I say, there's a simple case. The simple case is, suppose I have dilute phenol in water. So maybe I have a curve looking however it looks. But if I'm only interested in dilute phenol, I might be willing to draw a line through here like that and say I'm only interested in this down here and write y equals mx. If I write y equals mx, I obtain a formula like this: log L over L0 equals 1 over m minus 1 log x over x0, or L over L0 equals x over x0 to the 1 over m minus 1. M is simply the slope of the equilibrium curve at the origin. Now I've got a Lx formula that I can plot with no problem. So that's a case where you don't have to do anything tricky. You get your L versus X equation directly. Yeah?
Sorry, what is that squiggle? 1 over squiggle minus 1?
This M is the slope of the, well look, we'll use squiggle. Don't get disappointed. This M is the slope of that line. Okay? I happen to love squiggle. This is squiggle. Now hold it. Now hold it. That's really not squiggle. We'll call it squiggle, but it's really not squiggle. This is squiggle. This is squiggle-iggle. But we'll call it squiggle because I won't have any use for this, I suppose. Or if I do, I'll call it by its right name. Okay, now, so we've done the C equal 2 case, and there are several things we ought to comment. This is the plain vanilla problem. We can jazz these problems up in order to see if people can write equations. And so that'd be the only reason to do it. So there's a bunch of problems you could consider. This first one is actually practical. So I've said all along that I've got this pot here, and I'm